Yes, sir.
Thank you, sir. Welcome everybody. This is going to be the last one of the conference for this session. And our speaker is Sweta. She is from Thapar Institute of Engineering and Technology, Patiala, India. And she is going to talk on mathematical modeling and simulation of mechanochemical effect on two-phase transformation. Sweta is over to you. Thank you for providing me this opportunity. So here is the outline. Here is the outline of my today's talk. I will begin with the introduction, where I will explain few biological terms. Then I will go to the model, two-phase model. I will present this in more simplified and dimensionless form that consists of not coupled system of nonlinear partial differential equation. Then I will discuss the numerical results obtained through solving this system of equation. Then I will conclude by giving the summary of our work. And I will present at last. I will present the references. So to begin with, I will begin with the term avascular tumor. So avascular tumor means the tumor which have no new formation of blood vessels. Only the cell will multiply itself and they will accumulate at one point. So what happens then? Like if the cell gets overcrowded, the inner region of cells lack nutrient because the nutrient is diffusing from the boundary one. So the inner region of the tumor with lack of nutrient, due to lack of nutrient, they will try to migrate either on indirect basis or in directed motion. So they will exhibit indirect and directional movement. So what we are trying to include in our model, these migratory behavior of tumor cell in two-phase media. So the model consists of the model variables are cell volume fraction denoted by alpha, cell velocity denoted by U alpha, nutrient concentration denoted by C, and width of the tumor denoted by L. We have taken spatial domains that is denoted by xi, that is contained between 0 to L, and the time tau, that is between 0 to t, that t is final time. There are some general model assumptions that there is a continuous exchange of cell and fluid phase due to cell division and cell death. Mass and momentum are internally conserved. Nutrient transfer through the tumor is controlled by diffusion. Then I will move to the term chemotaxis. So what is chemotaxis? Chemotaxis is the directed movement of cell in response to external chemical gradient. So if we visualize this figure, we can see the tumor cells are overcrowded here. So the inner regions they are trying to migrate in search of nutrients. So some are migrating in the indirected way, and some are in direction of the nutrients. So that shows chemotaxis phenomena. Chemotaxis phenomena is not new. It is already studied in different scenarios of tumor growth, like migration of invasive cancer cells, tumor-induced embryogenesis, invasion of macrophages into tumor. Indeed, Moreover, Werner adopted multi-phase phenomena and expressed the chemotaxis and random motion term for a colony of the cells that exhibit growth. So our plan is also to exhibit chemotaxis and random motion for the migration of tumor cells in two-phase medium. So now we will present our two-phase model. So it consists of nonlinear partial differential system of nonlinear partial differential equation. So the first our variable is alpha volume fraction equation. So the volume fraction equation is presented in this way. The first in the right hand side, the first term denotes the random motion. That is the undirected motion of the tumor cell. These two are the birth and death term of the tumor cell regulated by the nutrients. So if there will be less nutrient present, the tumor cell may die. And the last term is chemotaxis term we have accounted. So this shows the directed motion of the tumor cells in the direction of the nutrients, gradient of nutrients. The choice of chemotaxis we have made that was made in the analogous to bacterial chemotaxis. Delta 1 here is the chemotaxis coefficient, D1 is the diffusion coefficient, and this is nutrient dependent cell growth and cell death. S1, S2 and S4 are the constants that regulate cell growth and cell death. The second equation is the nutrient equation. This is given by quasi-steady state nutrient equation. The right hand side of the equation denotes the nutrient consumption rate, where Q and Q2 constant are constant that regulates nutrient consumption. The third equation is the velocity equations. Here in the right hand side, these two are the pressure terms. The first term is the pressure due to the intercellular cohesion, and this term is the average pressure due to water phase, fluid medium. Because we are taking two-phase medium, so one phase is cellular phase and second phase is the fluid phase. So here delta 2 and D2 are constants that we have derived during our model formulation. Mu is the viscosity, K is the interfacial drag coefficient, alpha star is the constant that controls the stress in the cell phase. Now the fourth equation is the tumor width equation. Here, the tumor width is directly proportional at the boundary. Tumor width is directly proportional to the velocity at the boundary. So it is defined by these OD equations. Now we present the initial and boundary condition. So we have taken L. We have fixed L is equal to 1. So earlier it was moving boundary. We have fixed by the change of variable L is equal to 1. Then initially we have defined alpha is equal to alpha at tau is equal to 0. Then at the boundary we have defined alpha is equal to boundary condition for alpha. Then we have assumed that there is a continuity of a stress at the boundary. So the velocity at the boundary is defined by this term. And we have assumed that the nutrient concentration at the boundary is constant, that is given by C is equal to 1. So in order to solve this equation, we have used finite volumes and finite element method. So cell volume fraction equation is approximated using finite volume method, and cell velocity and nutrient concentration equation is approximated using finite element method. So now we will move to the results obtained by solving this equation. So first result, before that I have taken some parameter. So we are studying the influence of delta 1, the chemotaxis coefficient, delta 2, D1, diffusion coefficient, and D2. So we varied this parameter from ranging from -1 and 1 and obtained the result. And few parameters I have taken from the Breuer's paper, which is defined in this presented in this table. So we'll move to the result obtained. So the initial volume fraction is alpha. We have taken in the numerical simulation alpha is equal to 0.8. Final time we have taken 200. The time step we have taken 0.1. And the spatial domain from 0 to 1 is divided into 100 equal parts. So the first result, when is talk about the spread of tumor in chemotaxis alone, like we are varying only delta 1 and other parameter delta 2, D1, D2, I have assumed as 0. Then what happens? If we take delta 1 is equal to 0.1 and minus 0.1, so we see at the boundary all are accumulated and all volume fraction of tumor cells are accumulated at the boundary. But if we observe figure 1 and figure 2, the inner region, so the depth of this depth at final time, the cell volume fraction, presence of cell volume fraction is very the length is very less, and here the length is more. This means the water phase at inner region is expanding in figure B as compared to figure A. If we look at the final time. Now, if we see when we increase delta 1, positive increase delta 1 0.1, 0.3, 0.5, we see that as we are increasing, the growth rate of the tumor is slowly decreasing. And in figure 2, if we are negatively decreasing it in negative part. So we see the growth rate of tumor is decreasing and it is moreover moving linearly. So now figure 2, when we vary delta 2, we observe that the growth rate of tumor once when we are increasing, gradually they acquire the steady state. While if we are taking the negative of delta 2, the growth rate are going linearly, but as we are decreasing, the growth rate is also decreasing. Now we see the results when we have taken random motion alone, like that is we have varied the T2 and we have taken delta 1, delta 2, D2 0 and we have varied D1. So what we observe that in figure A, when we take D1 is equal to 0.1, we get the volume fraction here is 0. But when we take D1 is 5, there is no formation of necrotic core. That is, the dead cells are not forming the inner region. So from figure A to figure B, we see that there is a formation of necrotic core, but there is no formation of necrotic core in the inner region. So volume fractions are tumor volume fractions are equally spread in the whole area. Now we come to when we vary T1, as we increase, the growth rate is decreasing. Now we come to this figure. When we vary T2, there is no much effect in the growth rate, but we see that it is moving linearly. Now we have taken the combinations of all the parameters, like if we take delta 1 0.1, delta 2 0.1, D1 0.9, D2 0.1, D1, we observe this result. We can observe that the tumor is maximum at the boundary and the tumor is sparsely populated inside the region. And accordingly, the velocity is given and the boundary, the length of the tumor is given by figure D, and the oxygen concentration is given in figure C. So now, if we vary, we see that delta 1 is 0.1, delta 2 is 0.2, D1 is 1, D2 is 1. Then we see the opposite effect, like tumor is contracting, the volume fraction is maximum at inner region and at boundary, as we are moving at, especially the tumor are sparsely populated. And the velocity is given accordingly, and you can see that the length of the tumor is decreasing. So this was some important results simulation. So this is the summary of the influence of the parameter. Like when you increase the growth rate of tumor, when you increase delta 1, the growth rate decreases. When you increase delta 2, the growth rate decreases and acquires steady state. When you increase the T1, the growth rate decreases, and when you increase T2, the growth rate does not vary with increasing value, but overall tumor size changes linearly. So this is my summary of my work. Like the current law complements the previous scientific work by considering several effects such as chemotaxis and random motion of cells. The equation describes the evolution of tumor in presence of a nutrient that infuses to the tumor's periphery. The driving forces are created by nutrient concentration, chemotactic movement of cells, mechanical interaction between cells. The equations were approximated by the volume fraction equation was approximated by finite volume method using a print scheme to approximate the flux. Then velocity equation was approximated by finite element method, and nutrient concentration equation also was approximated by finite element method. So we saw the influence of the parameter delta 1, delta 2. D1 and D2 clearly that at some choice of parameters that you will expand, and for some choice of parameters you will contract. These are some important references. So the main reference was the Brewer's paper. From there we have extended our model, followed by the references. So Osborne and Bailey got the idea from the and the chemotactic curve for this we have taken on this paper.
Oh, maybe you can ask. So why did you take the finite volume for the cell volume and then the velocity in the first place? What did you?
Actually, the cell volume fraction for the FPM for the volume fraction, because the volume fraction equation is currently changing in hyperbolic and parabolic portion. Like if we switch on the switch off that delta 2 term, that equation will come, and D1 term, that equation will come converted to hyperbolic, and we switch on, that will convert into parabolic. So to manage the flux easy way, we have taken finite volume. That will be more difficult to manage with finite element, and other equation were elliptic. So the finite element goes suits well with the elliptic equation. So this is the reason for taking this. You can tell whatever the spaces you have, discrete spaces you have selected. This is in 1D actually. So so the discrete spaces are like this is 0 to 1, and I have been discretized into 100 equal. But you are using area. Yes. That is simple related.
So normally, okay. Some common sense.
Yes.
Even chemotherapy parameter increases. It should start from 0, because chemotherapy you have not given. There is already some growth.
Yes.
And then you give chemotherapy, and we
No, sir. We are not talking about chemotherapy. This is chemotaxis, and we are not including drug and anything. This is another term, chemotaxis. That means that it is directional movement of tumor cell in search of nutrient concentration, which is diffusing around the bound. Like nutrient concentration is available at the bound.
Yeah. So okay. Negative direction means what?
So
There is some positive quantity, there is some negative.
yes, the positive means, the negative means that tumor is contracting. Like if we are taking the negative, in the equation we are talking negative direction.
Yeah, negative. You see some parameter that chemotaxis delta 2.
Yeah, we have taken negative as well as positive. Like in the main equation we have accounted negative. So the positive will add that. That will add the volume, number of volume fraction.
So So, I mean, what does happen to the tube? The concentration is there on the periphery.
Yes, yes.
Okay.
Yes.
So, what you are saying, depending on the parameter, it will go down or go up. Go
Yes.
up means
Yes.
volume is increasing or not?
No, we have fixed the area like 0 to 1. The number of volume fraction, like if the volume fraction of alpha is increasing, then we have considered another phase, like fluid phase. Then the fluid phase will automatically decrease.
Yeah, volume fraction.
There is a moving boundary problem also we can extract, but that is very relatively challenging.
Yeah, it's better to apply same finite volume method for those.
Yes.
Our helpful leaders looking another. Yeah, this finite volume also.
Yes. The earlier fluids and volumes find a difference also. So this is information only. Is there any question on that? Okay. Let's thank Sweta again. We have to move to main seminar hall for closing ceremony.
One more quick announcement. The conference is planned on at 2:30. There will be a vehicle waiting near the VFR at 2:30. It will take you to Kormari. Thank you. Kormari.
Sorry.